So welcome to Math 331, the little questions. This is lecture 15. And what we're going to do today is we're going to finish up the pigeonhole principle, or at least talk a little bit more about some of it. So in the previous lecture on the pigeonhole, we talked about exercise A43, and this is from a book I wrote with my friend Ramin Taklubikash. If we choose 55 distinct numbers from 1 to 100, then among the chosen numbers, there are at least two whose difference is 10. And this is a standard type problem. We discussed as to whether or not 55 is actually required or if that's overkill. When I create problems, I deliberately do not want to use the best possible numbers. I don't want to give things away. There's a lot of things you can play with this problem. You know, why 55, why 100, why 10? What's the relationship between 10 and 100? So 1 is 10 squared is 100. Does that have something to do with this problem? I would look at different variants of this and try playing. If I keep the number 100 and I vary 10, how does 55 change? You know, 55 is a little bit more than half. 55 is also, I believe, 10 choose 1 plus 10 choose 2. And so you want to be aware when you're doing problems like this, you know, are there red herrings? Are there things meant to confuse you? So we've got 3 other problems I posted. If we have a subset, this is A42. If we choose a subset S from the set 1 to 2n with at least n plus 1 elements, then it contains at least 2 elements with A dividing B. Does that sound like fun? Okay. So again, much of today is to try to figure out thought processes. I have no idea if this is going to work, if I can actually highlight part of an image. No, I can't. All right. So I will just write it again. So we choose n plus 1 elements from 1 to ... 2n have at least one A dividing B. Whenever you see a problem like this, you always want to get a sense of how do the numbers relate to each other. Any thoughts between n plus 1 and 2n? So any relationship between n plus 1 and 2n? Where do you think that might be coming from? But it's n plus 1 elements and it's 2n objects. What's the relationship you think between n plus 1 and 2n?
2 times n plus 1 is greater than 2n.
So 2 times n plus 1 is greater than 2n. But for the previous one, you had 110, and you said 10 was the square root of 100. How would you view maybe n plus 1 relative to 2n? Well, again, these are general numbers. So let's look at it another way. So the problem says choose n plus 1 elements. Let's assume whoever wrote this problem is a minimalist. And they're trying to give you the statement that's just barely true. What do you think would happen if we choose n elements?
That'd be like 2n choose n.
Well, that's the number of ways we could choose n elements, is 2 and choose n. What do you think is the case if we consider a set of n elements? Do you think it's always the case that one divides another? Probably not. So if choose n elements, maybe the claim fails for a special choice. So you always want to get a sense of why they're choosing. What's the difference between n and n plus 1 relative to 2n?
One is,
Good, one is greater than half. So maybe the key is having more than a half. And so if it's more than half the elements, maybe we're putting things in pairs. Because if we have two n objects, if we put them in pairs, how many pairs would there be? There'd be n pairs. If have two n objects paired, we have n pairs. If choose n plus 1 objects, at least one pair has two elements chosen. And again, I'm trying to just highlight my thought process. So why n plus 1? What's the relationship between n plus 1 and 2n? Maybe it's not true with n objects. Where is n coming from relative to 2n? Well, it's half of that. And I'm talking about a dividing by b. That's like a pair of numbers. So maybe what's going on is I find some way to pair the two n objects. And I create n pairs. And now if I choose n plus 1 objects, and I only have n pairs, then at least one pair has two elements chosen. So my boxes will be a special set of pairs of numbers from 1 to 2n, and the pigeons will be the numbers, the n plus 1 numbers chosen. So the first thing is, can you give me an example of choosing n objects where we do not have any number dividing any other?
so all I would have to do.
So, right, so I need n elements from 1 to 2n that are all relatively prime to each other. If you had that many primes, yes, but you don't have that many primes. The number of primes actually percentage-wise goes to 0. So how should you get some intuition for this? What should you do? This is the Department of Mathematics and Statistics. Gather data, right? Default is gather data. What's the first n we can look at? N equals 1. This is going to be boring. So we'll have a set of 1, 2. Can you choose a set of 1 element such that, yes, yeah, either 1 or 2 works for no A divides B, because we don't have two distinct elements. It's really not that exciting. We could do now n equals 2. And now we have 1, 2, 3, 4. How many subsets can we choose of size 2? It's 6. Oh, in terms of how many that work, yes, potentially. So there's 6 ways we can choose. It's 4 choose 2. Or you can say I have 4 ways to choose the first number, 3 ways to choose the second, and then I have to forget about the ordering, so I divide by 2. So my possible sets are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. And I tried to write them in a good way. So for which of these sets will you never have an A divides B? Does 1, 2 work? So for the set 1, 2, is it the case that you don't have an A dividing a B? No, 1 divides 2. So 1, 2 fails. What about 1, 3? Oops. You can't have any 1s. So the 1s are easy to eliminate. What about 2, 3? Does that work? Does A not divide B? Yeah. What about 2, 4? No. What about 3, 4? So we have 2 sets that work, 2, 3, and 3, 4. Which of those constructions do you think will generalize nicely?
I guess we can try 2, 3.
We could try 2, 3. And so how would you view 2, 3 as 1, 2, 3, 4? And again, I don't care about the answer for this problem. I care about the thought process, talking about how would we get there. So how are you viewing 2, 3 as a subset of 1, 2, 3, 4? So describe it in words.
Second last element.
So you could do it as the second and the third last element. So that's viewing it with a very right-centric perspective. You could also view it as the second smallest and the third smallest element, a very left-centric viewpoint. You could also do it as it's the middle. Which do you think is going to be the more natural? Probably the middle. So if we look at n equals 3, we now have 1, 2, 3, 4, 5, 6. There's 6 choose 3 ways to choose 2 elements. This is going to be 6 factorial over 3 factorial, 3 factorial. Well, 6 factorial is 6 times 5 times 4 times 3 factorial. That cancels one of the 3 factorials. The 6 cancels the 3 factorial down below. So there's 20 things for me to write down. Do I have to write anything beginning with a 1? No. So I can eliminate all the 1s. And then we'll have 2, 3, 4, 2, 3, 5, 2, 3, 6, 2, 4, 5. I should have. All right, and then please let me know if I'm missing anything. So we have 2, 3, 4, 2, 3, 5, 2, 3, 6, 2, 4, 5, 2, 4, 6, 2, 5, 6. Those are all the ones where 2 is the smallest. Then we have 3, 4, 5, 3, 4, 6, 3, 5, 6. And then we have 4, 5, 6. Okay, so for the 2s, does 2, 3, 4 work? No, in fact, anything with a 2 and a 4 doesn't work. So I can kill that one, I can kill that one. Anything with a 2 and a 6 doesn't work. So I can kill the 2, 3, 6, the 2, 5, 6, the 3, 6. Okay, I'm going to assume everybody can just quickly look and see which ones don't work. And so we're left with 2 that work, 2, 3, 5, 3 primes, which is going back to your intuition of can we just do it with primes? The problem is there's not enough primes. And we should not have crossed off 4, 5, 6. I just realized we should not have crossed off 4, 5, 6. I got over eager. 3, 5, 6 we can cross out because the 3 divides the 6, but we can't do 4. So 4, 5, 6 should survive. And what about 3, 4, 5? Does that survive? Yes. So if you look at it, there really is no middle that's perfect here. You know, if I want a middle 3 elements, it's either 2, 3, 4 or 3, 4, 5. 2, 3, 4 doesn't work, but 3, 4, 5 does work. And so that's potential evidence for the middle. So this is giving us support for the middle. How could you view 4, 5, 6? Not the last n plus 1, almost. Well, we have 6 elements. This is the last, not n plus 1. This is the last n. So now we have enough to make 2 conjectures. They might both be right, they might both be wrong. And again, what matters is the thought process. Because it was not immediately clear to you how to find n elements such that they will be relatively prime, you were going through and we're looking at the data. We're taking small values of n, we're looking at which sets work, and we're trying to extrapolate patterns. So we have 2 conjectures. So we'll do conjecture 1. The middle works. And we'll do conjecture 2. The last n work. So for the last n, it's going to be the numbers n plus 1, n plus 2, ... 2n. Is it possible that any number in that list divides another number in that list? Well, for this list, if I have n plus 1, n plus 2 all the way up to 2n, is it possible that one number divides another? If you divide, if A divides B, then there exists an M such that AM equals B. What's the smallest M could be? Two, right? If A divides B, the smallest multiple B could be of A is 2. So smallest M, 2. So we know 2A, how must that be relative to B? Well, but we know that A divides B. So we know 2A has to be less than or equal to B. Because we know AM equals B as AM equals B and M is greater than or equal to 2. So since M is greater than or equal to 2, twice A has to be at most B. If you look at those numbers, n plus 1, n plus 2, etc., if you multiply any of those numbers by 2, what happens? What do you get? They're going to be greater than 2n. So any A in list has 2A at least 2n plus 2, so no A divides B. So the conjecture is true. So the last n numbers work. So when you see a problem like this, there should be a couple of things that are natural to try. Let me try all the numbers in the beginning. Let me try all the numbers in the end. Let me try the numbers in the middle. Let me try the primes. Let me try the odds. Let me try the evens. Some of these ideas are terrible. Evens is a terrible thing to try when you're trying to see, can I find numbers where A doesn't divide B? Oh geez, 2, 4, 6. No, God, this is horrible. Odds, 3, 5, 7, that's looking good, but then you have 9 and 3 divides 9. So quickly you eliminate odds, you eliminate evens. If you look at the very numbers in the beginning, you're going to have these problems from the evens and the odds. So now the natural things to try is the extreme left, the extreme right, and the center. Boy, can I make political jokes right now. I think the best I ever heard is, how many of you have taken physics? I had a physics professor who was liberal, who was talking about the integral of FDR when F was a conservative force. And so this is probably the only class you'll hear FDR talked about as a conservative force. But let's do the middle. Which middle do you think is going to be easier for n like 2 or n like 3?
Probably n like 3.
Why n like 3?
Which you probably just.
Well, look at how we did the middle when n was 2 versus the middle when n is 3. Where was it easier to find the middle? N equals 2, n equals 3. You're looking for the middle n of 2n objects. We had two choices. We had 2, 3, 4, or 3, 4, 5. What's the middle 3 elements of 6 elements? There is no middle 3. What's the difference between n equals 2 and n equals 3? Or between 4 and 6? There's a middle n elements. So which is the next n that will have a middle n elements? 4, 5 won't, 6 will, 7 won't. You want n's that are even. If n is even, then there will be middle n elements. So it might be when we're doing the analysis, it might break a little bit as to whether or not things are even or odd. And so, again, what I love about this class is I've always, every year I've taught this problem, I've always done the conjecture to looking at the far right. Yes?
Earlier I said that we want all and that are all relatively prime, but I just realized that's
Oh, yes, you're right. You don't necessarily want relatively prime. You just want they don't divide each other because 4 and 6. So I'm going to claim that that's why I crossed out 4, 5, 6 because you had said relatively prime and you had prime to me with that. And 4 and 6 are not relatively prime. As an aside, if you take the numbers 4, 6, 9, do we agree that these are all integers? There's a geometric progression to get from 4 to 6 to 9. So I multiply by r to get to here. I multiply by r again to get to here. What r do I multiply by? 3 halves. And so this is actually in a paper that was just accepted that I've done with some small students. We were looking at generalizations of this over the quaternions of sequences that avoided arithmetic progressions. And what's interesting is 4, 6, geometric progressions. 4, 6, 9 is in a geometric progression, but the ratio is not an integer. So you've got to be very careful when you say, I'm looking at sequences that avoid geometric progressions. Which kind of geometric progressions? Does this count as a geometric progression? It's not an integral geometric progression, but 4, 6, 9 are in a geometric progression. It's lovely when you have stuff like that to worry about. So let's look at the middle. Do we think the middle half will work? And I have no idea. I've never looked at this problem. So we have 1, 2, ... Let's take the case when n is equal to an even number just to make things easier for ourselves right now. So n is going to be 4m. ... 2m, 2m plus 1, ... 2n, where n is equal to 2m. So let's just try to do this case. So how high do we go? How low do we go? So 2m plus 1, how much higher do we go from 2m plus 1? Yeah. Well, how many numbers do we have to add on from 2m plus 1? So isn't it lovely trying to write things down carefully? So whenever I have a problem like this, I always just write down specific numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The middle is 8, 9, right? So here we have the case when n equals 8, 2n equals 16, n is 2m, so m equals 4. So I've got to go 4 elements in each direction. So that means 3 more elements here. and 3 more elements here. So I think I go to 3m minus 1. I'm adding m minus 1 elements to 2m plus 1. Oh, wait a minute, no, sorry, I think I go to 3m. I think I go to 3m. Right? It's the other one. I go down to m plus 1. Because if you look at this, I go all the way down to 5, and the one before that is just m. So this is what's going on in a special case. So I have the numbers from m plus 1 all the way up to 3m. Is it possible for one number in that list to divide another number in that list? Okay, which number can divide which number? So 12 and 6. So you've just found 12 and 6. So then the question is, will that be able to expand? And can you do that in general? And can we also do that in the case when it's not n is even, when n is odd? So can you give me 2 numbers that you think one should be able to divide the next? So we note 6 divides 12. And saying thank you so much for choosing numbers at basically the extreme, which could be problematic. But again, as things get larger, those are no longer necessarily at the extreme.
Also try to
So, but again, 5's at the extreme.
For those first sensitive, I guess they're just like all standard numbers where there's like a uniform amount of space between them.
Mhm.
But when you have numbers like, 1, 3, 7, 12,
If you're choosing your set, you can choose anything you want.
okay. So I'm wondering like how this property would be a set where there was different distance between each number.
Well, it would make, we would not be able to do the analysis we're doing right now.
Yeah.
But the problem is if you have longer gaps, you're going to then get clustered more towards the end. So maybe what you could do is you could have a couple of well-chosen numbers in the beginning, a huge gap, and some well-chosen numbers at the end. Maybe you have a bunch of odd numbers at the end and a couple of even numbers in the beginning. So a natural question might be, what fraction of the sets work? But so one way I might try to generalize this is, how would you relate 6 to m? I might say 6 might be, in this case, m equals 4. So how would you relate 6 to m?
Say like 6 equals m plus 2.
Yeah, so maybe consider m plus 2 and 2m plus 4. Or to be safe, maybe m plus 3 and 2m plus 6. And if m is sufficiently large, these will be less than 3m. So I think the conjecture of the middle is going to fail. It's a large enough region and there's a big enough gap. The numbers in the very far left of the region of size m and the numbers in the very far right of size 3m, we can multiply by a factor of 2 and still be inside the region. We won't find a multiple of 3. We won't find an a dividing a b where it goes in 3 times, but we should be able to find something where it goes in 2 times. So this conjecture is false. And this one here is true. So again, this is giving us some intuition about the problem we're trying to do, that if we tried with just n elements, it's probably not going to work. With n plus 1 elements, it should work. And we always have to figure out, what are the boxes, what are the pigeons? The pigeons are clear. Usually the pigeons are the easier thing to discover because they tell you, we have this many objects. You've got to be a moron. This is going back to physics, like there's protons, electrons, neutrons, muons. It's another type of particle. if you can't figure out what the pigeon is. The box, that's the hard part. So we need to find a way to split the numbers 1 to 2n in pairs. And in those pairs, one number has to always divide the other. So can you think of how to take the numbers from 1 to 2n and split them in pairs where the smaller always divides the larger, and each number is in one and only one pair? Good. Except don't use n because we're using n for the largest. Wait, just use a letter other than n.
Like A.
Good. 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 So for boxes, try we'll try A and 2A.
Sure, yeah.
So would that work? Where A is an element. The problem is if we tried to do that, we would then get 1, 2, and then the next one would be if A is 2, we would get 2, 4. We're using 2 twice. We could, but and again, we know we don't want to choose 1.
Yeah.
Because if we choose 1, so we could try to do stuff like that. So this is where things get hard, is to try to figure out how to do the boxes. And again, you're almost never going to have a class where you can have this many mistakes made in a 50-minute lecture and go down this many false paths. You learn a lot from seeing which things fail. I'm going to risk a cultural reference. Chitty Chitty Bang Bang. Anybody ever see that movie? There is a song from the movie Chitty Chitty Bang Bang. It's with Dick Van Dyke. There are rumors that I think Phil Collins was one of the little kids in one of the scenes. But there is a song called Throw the Roses of Success. For every mistake you make, be grateful. That's a mistake you'll never make again. If only people learned from their mistakes. But the idea is you learn a lot from trying things. So this was a fail. Here's another thing we could try. We could try 1 and n plus 1, and then 2 and n plus 2, and then 3 and n plus 3, all the way down to n and 2n. Would that work as a set of n objects?
Well, it'd be nice because n plus 1 is dividing. So we both like the case that we saw with 1, 2, and 2, 4.
We're trying to force it so that we have n boxes, that each box has to have the small element dividing the larger. Will the small element always divide the larger here? Not necessarily. So for example, if n equals 8, we would have 1 and 9, and then 2 and 10, and then 3 and 11, ... And this is another fail. Smaller, not always dividing the larger. So the problem is we need to split things up in such a way that every element is in one and only one pair. And in each pair, one number divides another. So you need the following observation. I can write any x as 2 to the k times 2m plus 1.
Slightly confused on why we satisfy A plus B.
Well, because we would have n groups, and we're choosing n plus 1 elements. So that means one group would have to have 2 choices. And if every group has the smaller dividing the larger, then if we choose n plus 1 of the n+1 elements from n groups, at least one group has to have two elements chosen. And that will give us the A dividing B. So can we somehow use this fact that I can write any number as a power of 2 times an odd number? How many odd numbers do we have? I'm sorry? We have n odd numbers. So maybe I was wrong with trying to form good pairs. So when I was trying to put things in pairs, that's a nice way to do it, because if I can do it in pairs, then the problem is trivial. But am I able to split up the 2n objects into pairs? I don't know. But here's a nice observation. I can write any number as 2 to the k times an odd number. Now imagine two numbers have the same odd part. If x1 equals 2 to the k1, 2m plus 1, and x2 equals 2 to the k2, 2m plus 2, and without loss of generality, we can assume k1 is less than k2, what can we deduce? We know x1 is less than x2, but we know more than x1 is less than x2. So they have the same odd part, and one of them has more powers of 2 than the other. X1 divides x2. So this is telling us this is how we should do our boxes. The boxes should not be splitting the numbers into pairs. It should be splitting the boxes into what's your odd component. Because it doesn't matter how many numbers I have in a box, as long as they all have the same odd component, if you order them from smallest to largest, they'll just keep dividing each other. To me, it was natural to try to break the problem into pairs, because I know if I have n pairs and n+1 objects, one pair has to be hit twice. And if I could just split the numbers, but I don't think I can. Yeah. You give me a prime that's too large. You give me, let's say we're looking up to the number 20. You give me the prime 17. There's nothing I can put in the box that 17 divides, or that divides 17. There's no way to do this. So this was stupid. So stupid, impossible. If p greater than n is prime, then no pair PB or AP with one divide other. So the attempt to split it into pairs where one divides the other, it would be wonderful if we could have such a splitting. It would be wonderful if we had such a decomposition. The problem would be trivial. The difficulty is no such decomposition exists. And if I look at a prime that's larger than n, if you double it, you're beyond 2n. So you can't have p being the smaller number. If p is the large number, there's no a that divides it other than 1, but then it only works for one prime, and we would have more than one. So can do once with a equals 1, then trouble. All right, so do we understand why this is not going to work? And so now what we want to do for our boxes is we're going to have the 1 box, the 3 box, the 5 box, and then the 2n minus 1 box. So now we have n boxes. We choose n+1 numbers. 1 box is chosen twice. So maybe it's this box that's chosen twice. And now we win. So do people see how this now works? The key idea is you have to look at the boxes are coming from the odd factor of your numbers from 1 to 2n. This is what I mean by pigeonhole principal problems can be hard. You have to be able to identify what is the box. Is it worth asking, do you remember your sequences in series?
I think so.
Okay, do you remember your sequences in series?
A little bit.
So if I want you to use the ratio test, it's not really that hard to figure out what to do. Let me take the ratio of an plus 1 over an and try to take the limit. If I want you to do the root test, I take the root. These are very easy to do. The comparison test is much harder. You have to have some artistry to figure out what should I compare it to. And sometimes you manipulate things a little bit to find a good thing to compare it with. So here, it was not clear what to choose for the box. The pigeon is obvious. It's, I've got n plus 1 numbers. Those are my pigeons. These can be extremely hard problems. Once I tell you this is the box, then it's not that bad to follow the argument. But the difficulty, the challenge, is seeing what to look at. And this is why it's the baby crying school of mathematics. You try a bunch of things until hopefully you find what comforts the baby. What can I do to try to find? I want to try to get some intuition of where things are coming from. I want to try to get to some intuition. Whenever you have a problem like this, take one fewer element, and then you should be able to find a counterexample. So then once you get that one extra element, it should be enough to prevent this from happening. What counterexamples do we have? So here are some potential research questions, which I don't know if any of these have been done. But so research questions. If take n items from 2n, what is the percent of times have A divides B for some AB in the set? So we just showed that it's possible to come up with sets that don't work, right? If we take the last right, the rightmost half, that fails. What's the probability if I choose a random set that there will be some A that divides B if I choose n plus 1? Does this go to 100% as n goes to infinity? What do you think? Do you think almost every set will have at least one A dividing a B?
I'm not sure actually.
Right, but what's the odds of that? So how many sets are there? There are 2n choose n sets. So this is 2n factorial over n factorial squared. Do you know Stirling's formula? No, that's something different. Stirling's formula talks about how fast the factorial grows. So Stirling's formula says m factorial is about m to the m e to the minus m square root of 2 pi m. And so you can use this to estimate how fast 2n choose n grows. We could also do some trivial estimates. And again, I'm a huge fan of trivial estimates. Can somebody give me a number that's larger than 2n choose n? Where do you see 2n choose n? What theorem are you thinking of? What kind of number is this? This is a binomial theorem. So if you look at 1 plus 1 to the 2n, this is just one of the terms in the expansion. So we know 2n choose n is at least 2 to the 2n. With a little bit of work, you can actually show that this is the largest term. And so this is going to be greater than or equal to 1 over 2n plus 1, 2 to the 2n. So this gives you, a really quick estimate of how quickly the number of subsets is growing. So I agree with you that there are going to be a lot of subsets that don't work. I can take my, rightmost half and maybe tweak a little bit carefully. But if I do that, maybe percentage-wise, there won't be that many. So one question is, does this go to infinity as n goes to infinity? If yes, how quickly? So again, there are many more research questions you can ask. One of my goals in this class is to recruit for small and to just give you a sense of how do I work, how do other mathematicians work. We take stuff we're doing, especially if you're at a liberal arts college and you're teaching, you need to multitask. Can you get a research problem from something like this? Almost surely people have thought about stuff like this, but maybe not. A lot of times questions are just not asked. And if you can get in the habit of asking good questions, you can do some computer simulations. The next is the structure of, we'll say, these bad sets. We know the far right works. We know the middle does not. What if I do some kind of combination, we'll make peace on earth of the far left and the far right? Can we find a way to bring them together? Can you give me an explicit construction that works? We did an explicit construction just looking at the far right. What about in general? So again, if you ever want to think about stuff like this rather than the standard homework problems, that's absolutely fine. The goal of this class is to be a springboard. This could easily become a great paper to do for fun. This could become a great project for small. This could be something you do on your own. I'll stop here. I'm happy to just chat a little bit more because I know it's after time now. So, but this is what I love about this class. I had absolutely no idea where we'd go to today.